You can try.
In part 1 on electromagnetism, we have seen that changing magnetic field induces current.
I reset the moment.
This induced current, according to Lenz's
on the
law,
ground, in
appears
position.
in such a direction
And
that it
I try to
opposes
put
the
this
change
lumpy
that
ring in
produces
between.
it.
If I just put on,
The result is this aluminium ring gets repelled.
an interesting experiment. I'll put this, switch on. Why it is not levitating?
So, because maybe it's thin.
Thin. Okay, I'll put a thinner ring. This is levitating.
Yes, sir.
Take it out. Can you make out? What is the reason?
So there's a cut over here.
There is a cut over here in this ring. And the circular effect of this ring is not here. There was a current path, continuous, where the path for the current is broken. As there cannot be any current flow in this, there cannot be any magnetic field produced by this, hence there is no levitation. Whereas all the things are perfectly available here, that's why there was levitation here. Now, the type of current that is created or induced in this is concentric. That means all their centers are same. This can be verified by putting these concentric rings. The field produced by the first ring must attract the field produced by the second and third and so on. So if we put all these rings, they must remain like one plate. Just drop this. You drop this.
Whether the current flows or not, the electromotive force or voltage is induced in the aluminium ring. Faraday's law expresses this induced electromotive force by this equation. The induced electromotive force is equal to the negative rate at which the flux through the coil is changing. Let us further examine the nature of the induced electromotive force.
Here is an electrical coil. You have taken a long, thin, super enamel wire, given 2300 turns, connecting this coil to a wire, and through this plug top, 230 volts alternating current can be given in this coil. At the center, there is a magnetic core. As the idea is, the field produced by this can be extended up to this. We have just, the magnetic field is available here. There is more here. There is much more at the bottom. If I place it here, we find more and more magnetic flux cutting this, giving an indication of more and more energy conversion. I have here another electrical coil. This coil has 30 turns. It is connected to a bulb which is designed for 12 volts. If I pass the magnetic field of this in the center of the coil, what must happen to the bulb? Let us see. A little magnetic field, more, and finally, what must be the voltage you must be getting here? This has 2300 turns connected to 230 volts. There is a regular ratio. Every 10 turns is responsible to accommodate 1 volt. Has it got any relation to this bulb and the voltage in the turn? We have 30 turns. Therefore, we get 3 volts here because we have taken a ratio of 10 turns per 1 volt. Naturally, I remove this coil and put another coil. This has 100 turns. With this 100 turns, the voltage is 10 volts. So, with more and more number of turns, more and more voltage we get. So, this is another great use of the AC magnetic field, that is transformation of voltage. How does it take place? Because the magnetic field produced by this coil interlinks with, and depending upon the number of turns and the amount of flux that is linking, it induces the current and thereby this. And this is called electromagnetic induction. We have here, naturally you can see the difference, 30 turns, 3 volts, 100 turns, 10 volts. I have used two different coils. If I want to have different voltages, it is not at all necessary. I can use a coil with many steps in it. Why don't you just touch and tell what are the voltages? This is
3 volts,
3 volts,
6 volts,
6 volts,
8 volts,
8 volts,
10 volts.
10 volts. This, the primary winding, we call this as the secondary winding, and this entire thing, we call it a transformer. What is a transformer? It is nothing but an agency to do the transformation of voltage by using the principles of electromagnetic induction. If you give 230 volts here and take less voltage, we call it step down transformer. Give 230, take out 230, we call it 1-to-1 transformer. Give 230 and take more voltage from what we give, we call it the step up transformer.
Thus, we see that there is a definite relation between the voltage and the number of turns on the coil. This can be expressed by the following equation. Voltage applied to primary divided by voltage induced in secondary is equal to the number of turns on primary divided by the number of turns on the secondary.
I have here two tiny coils. This has 30 turns. This coil also has 30 turns. I have connected them in series and their output to this lamp. If I pass the magnetic field in the center of the coil, this is equivalent to one coil having 60 turns. What will happen? Naturally, 60 turns gives us 6 volts. Another interesting thing it is teaching us is the simple arithmetic. Now this is 3 volts. What we get by reversing this coil, it is 3 minus 3 is equal to 0. And again I reverse it, 3 plus 3 is equal to 6.
With this experiment, it is clear that the induced voltage has definite direction. Therefore, by interchanging the direction of the coil, we can either add or subtract the voltages.
Here we have two transformers. In this transformer number 1, this is the primary coil, these are the secondary coils. Together they are giving 6 volts. And this is connected to the primary winding here and the secondary winding here, giving us 9 volts. The primary to secondary, primary to secondary. The magnetic field linking this, giving us 6 volts. The magnetic field produced by the primary coil here, linking the secondary coil, giving us 9 volts. This is how from electricity to magnetism, magnetism to electricity, electricity to magnetism, magnetism to electricity, the conversion goes on. Right from powerhouse up to our houses, by through umpteen number of transformers, this is how the energy is converted either by step up or step down or step up various transformers, and we ultimately get the voltage in our houses. This is transformation based on electromagnetic induction.
The natural question that follows is, how does the transformation affect current capacity?
Over this primary coil, if I connect another coil which is having 23,000 turns, the turns ratio is increased 10 times. So while applying 230 volts, what I get is 2300 volts. The voltage is stepped up 10 times. If the primary has a capacity to adjust itself for 1 ampere of current, what is the current handling capacity of the secondary coil? It's a very interesting thing. As the voltage is stepped up 10 times, the current handling capacity of the transformer goes down 10 times. This is because the volts and amps, the product of volt and amp in the primary winding is almost equal to the product of the volt and amp in the secondary winding. Leaving alone, of course, due to some losses. I am not touching that. So, at higher and higher transformed voltage, the current goes down and down in the reverse ratio. If that is so, if I go on reducing the voltage of the secondary, the current handled increases. If I say I connect here a 23 volt coil, I can get up to 10 amperes. A coil of 2.3 volts may give us 100 amperes. Another advantage of the AC field, therefore, through a transformer is the high current we can obtain at lower voltages. Just to show that, I have here a small example. I have a tiny coil which has 30 turns. Just for interest's sake and academic purpose, I do not connect any load except a fuse wire. If the current is more than, this is a 20 ampere fuse wire, if the current flow in this is more than 20 amperes, naturally this fuse must blow. Let us watch. I will put it in the circuit. Just let me switch on. 1, 2, please watch here. 3. The fuse has blown, giving an indication to us the current is more than 20 amperes. Let me try with a higher rating fuse of 30 amperes. With this 30 ampere fuse, I'll try 1, 2, 3. Oh, this also has blown, but taking little more time. This is what is called the timing of fusing. In place of it, I'll put still a higher ampere current fuse. This is of 40 amperes. Let me start this. 1, 2, 3. Yes, it is able to adjust itself. That means the current flowing through this little coil is more than 30 ampere and less than 40 ampere. Now, in spite of this low voltage, high current has entered in so many fields. Let us see some of the utilities of it. I am just, instead of just passing the current through fuse wires and blowing it, I am connecting this low voltage, high current to an element, a nichrome element. You can see that it is getting heated up and working as a quick heat soldering iron. This is how the quick heat soldering iron is made. Even our polythene bag sealing machine has this low voltage, high current system. There is a long strip. This technology has entered in a very big way, or even our pawn shops. So in every lane you will find a pawn shop where for lighting the cigarette, this engineering has gone up to that pawn shop. Not only that, this low voltage, high current, another interesting advantage is this. There are 2 carbon electrodes. Just to show you an idea, what we get in this is an electrical arc. Where do we generally use it? You must be knowing the electric arc welding. In that electric arc welding, we have a welding transformer. It has got several tappings, 100 ampere, 200 ampere, 300 ampere. Two leads are taken out. One is connected to the body, the other is connected to an electrode, and when we strike the electrode, a high arc is established, the rod melts and joins both the bodies. We say the job is welded. The same system of arcing is used in cinema arc lamp also to get the bright light so that it can pass through the film and give us the images which we are enjoying in our theaters. One small gadget here, again a low voltage, high current. It deals with a higher current as compared to this. That's why its body size is more. If I pass the magnetic field through the center of this current is passing through the nichrome wire. Can I take an advantage of this? Yes, we can cut this thermocol piece comfortably without having any edge defect. What I mean by edge defect is, if you use a knife, you'll get a lot of grains coming out. But this is a very, very smooth cut. Now, as I increase this increased gap, I'll remove this, I'll give full magnetic field on the coil. Naturally, the voltage induced is more, the current increases through this resistance here, and I can even cut an acrylic sheet. I'm just making a straight cut.
The experiment can be concluded with the simple equation that power intake from primary is equal to the power output from secondary. In the first part, we saw that the flow of current is accompanied by magnetic field, and that changing magnetic field produces electromotive force. However, to bring about the change in magnetic field, either the magnet or the coil has to be moved. The experiment with the transformer shows that no such physical movement is necessary. Time-varying magnetic field produced by alternating currents is capable of producing electric field and vice versa. In fact, this is how the electromagnetic waves or radio waves travel through space.